Our solar system is a wondrous place with a single star, our sun, and everything that orbits around it: planets, moons, asteroids, and comets. What do we know about this beautiful solar system we call home? It's part of an even larger cosmos with billions of other solar systems.
Hi, I'm Jim Green, Director of Planetary Science at NASA, and this is Gravity Assist. I'm with Faith Vilas of the National Science Foundation, and we're here to talk about everything Mercury. Faith has been one of the original Mercury researchers well before the famous Messenger mission. So Faith, how did that happen? How did you get involved in Mercury research?
Well, I was an undergraduate and I was working with a professor over at MIT, and I wanted to do some independent study as an undergraduate student. And he suggested I take a look at Mercury. And Mercury is not an easy object to observe from the Earth, either from the surface of the Earth or even from something like the Hubble, because it only goes at most 28 degrees away from the sun. So it's sort of one of those projects that you take on and you're going to do it, and you're standing on a ladder and you're tilting your telescope over near the horizon and you can barely see it. And, you can pick it up and you can follow it a little ways or follow it up or follow it down, but it's always near the sun. So you always have to watch out for the sun. And so it becomes a tricky problem to observe.
Yeah, some of that original research on Mercury, you weren't alone. There were others that got excited about that planet. As our closest planet to the sun, as a terrestrial body, it's important for us to study it. It tells us clues about planet formation. So you made a number of predictions, the scientific community did, before we actually were able to get a mission together like Messenger to go to Mercury. What were some of those things that proved to be correct?
The prediction that I made that proved to be correct, which I'm grateful for, was that there was no iron oxides. There was no oxidized iron in the surface material of Mercury. They have a very characteristic spectrum that we can see across our visible spectral range, visible and near infrared, and we were not seeing that. And I said, I don't see this. It's just not there in enough quantity to say that we have something on the surface of Mercury. This flies in the face of the fact that Mercury, we do know that Mercury is very heavy. It has a very large core. It's likely an iron and nickel metal core. And every prediction is that it was going to have, plenty of oxidized iron in the surface material. And every prediction was that. And I said, no, I don't see it. And we get there with Messenger, and sure enough, it's not there. And the reason people said, well, you may be wrong, is again because Mercury is so close to the sun and it's so hard to observe. If we're looking at it again from the Earth, we have to look through a really thick atmosphere down near the horizon. It varies very quickly. It could affect your spectra if you're not being very careful about your observations. And because it is so close to the sun, we can't take something like the Hubble Space Telescope and turn it toward Mercury. It's too close to the sun. If the Hubble passed the sun and it got fried, that would be the end of not only Mercury's research, probably my career.
Yeah, in all of astronomy.
Yeah, no
Hubble's
kidding.
been so successful.
It's been hugely successful, but it can't observe something that close to the sun. So it needed Messenger to be able to solve that. But that was certainly my prediction. The atmosphere, we were pretty sure, once we started to discover the atmospheres, we were pretty sure of its content.
Well, was there any indication that there could have been ice on Mercury from ground-based telescope?
Yes, there were, of course. And that came from ground-based observations with the radar at Arecibo in Puerto Rico. And the observations were made, of course, near the poles of Mercury. And the first indication was, this looks kind of like it's very different. Maybe it's a signature that we would expect to see maybe from water or water ice. And why would this be there? And then they continued the observations. They were able to, with improvements in the radar, they were able to narrow them down to specific areas on the poles, the North Pole and the South Pole. With the images we got from Mariner 10, they were able to correlate, show that some of these signals matched where the craters were. And so we were thinking, okay, what's going on here is that we have craters in the poles that are in the shadows because of the poles. The craters themselves are in the poles, near the poles in shadow, because Mercury doesn't tilt very much on its axis. It's pretty much upright. So the sun never reaches them. And since the sun never reaches those locations, they can keep water there, ice is there as long as they want to keep water and ice
forever.
there. And so the question became, where did it come from? And it largely looked like it came from sources outside of Mercury, like because Mercury is so close to the sun, everything is going to be focused into crashing into it. And comets with water ice and comets came in and
impacted
it and trapped a whole bunch of the water ice at the poles.
Yeah, as we've learned from messenger data, they did an outstanding job looking at the southern hemisphere.
Yes.
And mapping their craters and into the permanently shadowed regions and matching some of their other observations, which also indicated water. But they weren't able to really see the northern hemisphere.
Right.
But with the radar, we did.
Mm-hmm.
And so then that means, of course, by analogy, that the same thing
is going on
same
both
thing's
sides.
Going on both poles. Yeah, really exciting.
And with some very, I think, creative ways of observing the southern hemisphere, we were able to look at the structure inside the craters that are not lit. From other things that had come out of them, we could see and delineate the structure from the Mariner 10 observations. It was truly a good piece of work.
Did we have some predictions that Messenger showed didn't pan out?
Did we have some predictions? Well, of course, things that were predicted, of course, included the iron on the surface that we did not see. Things that were not predicted were a lot of the other materials that we did see, both through the ground-based observations but mostly through experiments we had on board Messenger that could look at the elemental compositions, not so much the spectral compositions, because the spectra were pretty bland, just as I predicted many years before, for the surface material, except in a couple of places where we had some really unusual features and bright features with sulfur that we assume were sulfur, features that we have not yet fully explained. But one of the things that was in question, I don't know that it was not predicted, but it was in question when we went to Mercury, was the question of whether there was volcanism. Did we have volcano activity type of thing on Mercury? And we sure did. The whole thing has got flowing volcanoes at different times.
Huge basins, like
huge
basins.
Huge basins.
Material that's filled into the craters.
Yeah, we didn't have the really super high volcanic, mountains like you get on Mars and we have on the Earth, but there's obviously a lot of volcanic activity on Mercury. Mercury was not a dead, cold planet. Mercury was a very active planet at some point.
Well, this, of course, led everyone to think that at least some of the iron oxide would be coming up from below.
From below. And for whatever reason, we have not yet seen that. We do not see that. And, we don't see any flows of our major activity on Mercury at this point. But it certainly didn't occur in the past, or if it has occurred, it's been stripped away somehow or another in Mercury's past. Mariner 10 had shown that it had a magnetic field and that it had a magnetosphere as a result, of course, too, and it's close to the sun. But it did have a magnetic field, and it looked as if, for all that Mariner 10 could tell, that the magnetic field did change a little bit. From Messenger, we learned that not only does it change, but it's offset. It's not centered. The magnetic field that we have on the Earth is centered around our equator, sort of. And it's not absolute, but it's kind of centered at the equator.
Tilted a little bit,
but through the center.
Right.
Not on Mercury. Mercury's magnetic field is centered in the northern hemisphere. And that means that various levels of the surface of Mercury probably have some different levels of protection from the magnetic field. We have protection. We are all protected on the Earth because of the magnetic field at some level. And Mercury has this varying magnetic field that's offset from the center and is obviously there, but it's not clear why it's even located in that particular location.
Yeah.
What I'd say about Mercury is that everybody thought this was going to be a bland and boring little planet that didn't have anything much going on. And instead, as some of us predicted, myself included, every solar system object is different from everything else. It's not the same. I mean, Mercury is always drawn, people thought, it's going to look like the moon. No, it's actually significantly different than the moon, and they aren't absolutely the same. And one of the things that I have been fortunate in my life to have experienced is the first really, really good look at almost every planet in our solar system. I guess every planet now.
Every planet.
And every planet. And every planet, the comets, a lot of the asteroids, they're all vastly different. They're all much more energetic and have much more of an interesting history than we ever imagined. And so to predict that something is going to be, oh, it's going to be this way because it looks kind of this way, what we already know about it, is wrong, because it's always different. It's always different, and it's always new. And I've been fortunate to live through seeing the first really good look at these planets, and I predict that there's so much more we can still learn from them.
This is the field of comparative planetology.
Right.
And we are always comfortable about making predictions that can be seen from one body and extrapolating it to another. And when we find that that's not true, that uncovers the new physics.
That should give us a reason to have to go to these objects, because we're learning new things. And that expands comparative planetology to what's different and what is the same, and what affected what planet in what location in its solar system, or its system. That is also extended to exoplanets now, too.
One of the things, and you bring it up here with exoplanets, Mercury is that small body, is that small terrestrial body. It's smaller than Mars and certainly Earth and Venus. One would expect, although we can't see any or many of those in exoplanets, that's probably one of the more populous planets.
What we see that's really interesting with the exoplanets and just fascinates me is the number of exoplanets that are closer to their host stars, their star, in their planetary systems, that are closer in distance to their host star than Mercury is to our sun. And we still, I believe, think that Mercury did not form in its current location and was moved in toward the sun. So here we have this lack of these things, where we see these like big planets, Jupiter-sized planets, bigger than Jupiter, hot, very hot planets orbiting super quickly around their suns or their stars. Why are we seeing this? And and does this also play back into the huge amount of diversity that we see in planetary systems, not only in our own solar system, but in other planetary systems? We're learning so much about that now. It's so different and it's so amazing. And we're learning that planets are the norm and not the exception to the rule for stars.
This may sound crazy, but ever since I had learned that Mercury's core is so large, comparable perhaps to the size of our own, and the planet is very dense, it's almost like perhaps that was a core
of a larger planet.
Yeah.
And that has been a thought that's been around for a long time. It's certainly a good, viable thought. It looks like it could have been a core from a larger planet, that what we see in the way of the crust, quote unquote, around Mercury now actually is just the layer that was above the core when it, for some reason, was stripped away of the rest of its planetary surface. That might have happened in the very, very early solar system, when we had this what we expect now is a huge, violent migration of objects throughout the solar system. Things didn't just happily form in one place. They formed in other places, and then the sun and Jupiter and Saturn got busy and kicked everything, because they're so massive, kicked everything around in the solar system. And then, planets will hit other planets, things will fragment, asteroids will hit things, and Mercury may well have hit another planet formed elsewhere in the solar system, been hit and kicked. This core might have been kicked into its current location. That has been a thought about Mercury for a long, long time. I don't think we fully have the answer to that one yet.
Yeah, no, I can't wait for the answer to that one. The concept that the impacts and planet migrations going on has really led us to think about our small bodies, and to really get an inventory of them, really understand them, their distribution. And one set of small bodies called Vulcans, we're quite interested in finding. And what do we know currently about the Vulcans?
That we haven't found any yet. We have not found
So what
any
are
Vulcans.
they?
Vulcans are asteroids that are postulated or proposed to be around Mercury, between Mercury and the sun. And so far we've looked from all sorts of different and creative methods of finding these objects, and we have not found them. Not with MESSENGER, not with ground-based work, not with space-based work. But that's what the Vulcans are. And we've seen plenty of objects sort of between Venus and the Earth, and Venus and Mars, and then, of course, the very heavy concentration of asteroids between Mars and Jupiter. But our near Earth objects or are located sort of from the Venusian orbit outward, and then of course the ones that are potentially hazardous to the Earth are located in locations where they pass close enough to the Earth to be a potential danger. But we do not see anything really between Mercury and the Sun.
So
We've
some
seen
sort of
comets come through and crash into the Sun, but
Oh,
we
yeah.
have
all the time.
all the time.
Yeah.
But we haven't seen any asteroids in that area, which they'd be hot little.
Yeah, they'd be
dense
bright. They'd be
rocks.
bright in the infrared. They better
Yeah.
be, right?
They better be right.
Well, we also have to think about our solar system as a point in time.
Mhm.
As you point out, there's been quite a bit of evolution. And so when we look at other solar systems and the objects in their solar system, they are at a different point in time in the evolution. And so there's planet migration, there's things that happen over time where impacts are collecting the small objects, and finally solar systems completely calm down. One of the thoughts are that we still are an evolving solar system. You can tell because we have a zodiacal light, and the zodiacal light having comets come in, material still being spread around, material still falling on planets. It's not a dead system.
Not a dead system by a long shot. And my reaction to what you're saying to me is sort of mixed, because a lot of the objects that a lot of the other systems that we see with the exoplanets and around other stars, many of them are solar-like stars. Many of them are cooler stars, because we're looking for life. Ultimately, we're looking for life. Let's face it. So we would like to see if we can find some life elsewhere. So we're looking for the life that we know about, and so we've been looking for life as we understand it, which is kind of carbon-based and like us, sort of. We look for the types of objects that are like that, and our spacecraft data that have looked at these, like Kepler, looked at a group of solar-like stars. Our ground-based observations look at solar-like stars and the cooler stars, and sometimes I'm sure the hotter ones as well. But we probably don't see them way back in their formation unless they're just young stars. And we do have a variety of things that we see. We see disks of dust across around other stars, which is what we expected to see and what we think our solar system started out like. But now we're beginning to see some disks where we have gaps in these disks where planets have formed. The stuff is glommed together enough to form a planet or an object.
Yeah, the beginning of formation.
Beginning of formation.
Yeah.
And there's some absolutely stunning observations now being made that show, the dust around the other stars, but clearing areas where smaller planets are beginning to form. So what's going on with that? I mean, it's truly amazing what we're seeing. We're seeing all sorts of variations and different types of planets. We're seeing planets at different moments of formation. Things I never thought I would see in my lifetime.
Yeah, I know. It's really exciting. To me, it's like this huge puzzle for which there's a new piece that comes out.
There's
We have to figure out where to put it.
There's so much. Every day there's so much.
And it's not
more.
just flat. It's three-dimensional because it's different in time.
Yeah, it's different in time. And the further away we are able to look, the further away in time we're going to be looking, which to me is also absolutely fascinating. So we need to push this on further in my book.
Well, that field will indeed evolve rapidly.
It will.
And the importance of studying our solar system, indeed, is all about getting the knowledge we have about our own planets, in addition to comparing those with the exoplanets.
Absolutely.
And learning from that.
And my field, which started out so many years ago with just looking at Mercury as a point source in the sky, in the middle of the night standing on the edge of the ladder, is now turned into more geology, because we are able to look at so much of that surface. And so there's so much more geology and geological interpretations of things, where the planetary astronomy side of things now is shifting as much toward the farther reaches of our solar system, for sure, because technology has finally caught up with what our solar system is like, and we understand that it goes on beyond Pluto's orbit, and we have a huge amount of objects out there which we weren't able to see before. And the technology is now allowing us to look at these disks where planets are forming around other stars as we see it. We're just doing amazing things.
I'm Jim Green. I'm here with Faith Vilas, and we're talking about Mercury and its implications, not only in our solar system, but with exoplanets. You've led an exciting scientific life and you're still going strong, but what was really that gravity assist that got you interested in planetary science?
When I was in the second grade, somebody gave me a copy of a book called The Golden Book of Astronomy. And I got this Golden Book of Astronomy. We had not even had, neither us nor the Russians had any astronauts in space. But I looked at this and I said, I want to work on this. I want to work on these planets. I want to work on these astronomical things. I want to work on these things, galaxies, and I wanted to be part of this space program. I wanted to be part of this. I wanted to be part of our exploration. I wanted to be part of humankind going into space and support it and look at these planets. And I used to, sort of fantasize about studying these planets and these galaxies and these stars and these astronauts and these, winged, rockets that were going to go up. And they hadn't gone up yet. And they finally did go up, of course. And that's really what got me started in this. And from that point on, mixed in with some other things that I chose to pursue periodically a little bit as I was growing up, I always came back to, I want to be an astronomer. I want to be an astronomer because I wanted to study these objects. And so when I got to high school and then got to college, that's what I did. My family was a little bit nonplussed initially, and then they sort of got on board. And I ended up with, I think sort of parents that said, yeah, that's fine. Go do it. Go do it. Go do it. They've been happy with that. But it was in the second grade. It was the Golden Book of Astronomy.
Faith, I really enjoyed chatting with you about the science of Mercury. I really appreciate you coming and giving us your insight.
Well, thank you very much. I very much enjoyed coming and talking with you all too.
Join us next time as we continue our virtual tour of the solar system. I'm Jim Green, and this is your Gravity Assist.